Something massive may be controlling our solar system's edge. You can't see it. You can't photograph it. But its gravitational fingerprints may be everywhere. For decades, astronomers dismissed strange orbital patterns as cosmic coincidence. They may have been wrong. Tonight, we're following the evidence that suggests a hidden giant may lurk in the outer darkness. We'll discover how distant objects may reveal its presence through unusual alignments. Before we dive into this cosmic mystery, drop a comment about what you think might be hiding out there. If you enjoy these space investigations, consider subscribing. These deep space discoveries are meant to be shared. Astronomers expected chaos in the outer solar system, random orbits, objects scattered everywhere. Instead, they found something unusual. More than a dozen distant objects appear to be marching in formation. These cosmic wanderers live billions of miles from the sun, yet they move like synchronized dancers performing an unlikely routine. The mathematical odds make this scenario seem essentially impossible. Picture trying to get 15 strangers in different cities to accidentally show up at the same restaurant, at exactly the same time, wearing identical clothes, without any communication between them. That's still far more likely than what astronomers may have discovered. These distant objects maintain their coordinated dance across unimaginable distances. This synchronized behavior suggests something extraordinary. An invisible conductor may be orchestrating this gravitational symphony from the outer darkness. The evidence extends far beyond mysterious alignments. Objects in the outer solar system experience gravitational tugs that our mapped planets do not easily explain. Scientists have run the calculations countless times. They've accounted for Neptune's influence, Jupiter's massive gravitational reach, every other known body in our solar system. The math still refuses to balance. These distant objects appear to respond to a gravitational force that officially doesn't exist. Computer simulations reveal a striking possibility. One scenario can reproduce the observed orbital patterns with remarkable accuracy. A planet roughly 10 Earth's mass may be lurking unseen in the outer darkness. The gravitational disturbances suggest our solar system may contain a hidden architectural force more powerful than anything we've mapped. The most compelling evidence comes from objects that seem to have broken free from all known planetary influences. Scientists call these detached objects cosmic hermits living in the deepest isolation. These worlds exist so far from the sun that they've escaped Neptune's gravitational control entirely. They should move through space according to their own ancient rhythms, completely undisturbed by planetary influences. Instead, their orbits show signs of external influence. Take Sedna, one of the most famous residents of this region. Its closest approach to the sun is still 3 times farther than Neptune. From this cosmic exile, it should follow its own independent path through space. But Sedna doesn't appear to behave independently at all. It moves in striking harmony with other extremely distant objects. This coordination may reveal the hidden hand of a massive unseen world. Astronomers faced a mathematical mystery that seemed unsolvable. How could objects billions of miles apart maintain such coordination? The answer came from computer simulations running for months. Scientists programmed virtual solar systems with every known gravitational influence. They ran these simulations forward and backward through billions of years of cosmic time. The results kept pointing toward the same possibility. One addition to our solar system could create the observed patterns, a massive planet orbiting the sun at tremendous distances. The simulations suggested this hidden world might complete one orbit every 10 to 20,000 years. That's longer than all of recorded human history. Yet from this remote cosmic throne, it could shape orbital mechanics across billions of miles of space. Every computer model points toward the same intriguing conclusion. Planet 9 may exist. The hidden planet doesn't just influence distant objects randomly. It may conduct them through precise gravitational relationships called orbital resonances. These are like cosmic musical harmonies played out across billions of miles. In orbital resonance, objects complete their journeys around the Sun in simple mathematical ratios. One object might orbit twice while another orbits exactly 3 times. This creates stable, long-term patterns. The extreme outer solar system shows multiple resonant relationships. Objects that should have chaotic, unpredictable orbits instead move with mathematical precision. They may be locked into gravitational harmonies with something massive and unseen. This resonant behavior suggests the hidden planet may have been conducting this cosmic orchestra for millions of years. The gravitational relationships appear too stable and too precise to be temporary coincidences. These orbital resonances provide some of the strongest evidence yet that Planet 9 isn't just a possibility. It may be a gravitational necessity. Perhaps the most striking evidence comes from the directions these distant objects point as they orbit the Sun. Their orbital paths should be scattered randomly in all directions. Instead, they cluster within a surprisingly narrow range. Scientists measured the orientation of each extreme orbit. The long axes of these orbital ellipses, the directions they point through space, show unusual clustering. The statistical odds of this happening by chance appear extremely low. Imagine throwing darts at a dartboard while blindfolded. You'd expect hits scattered all over the board. But if every dart clustered within a narrow slice, you'd know some hidden force was guiding them. The orbital directions reveal the same thing. Some massive object may be gravitationally sculpting these paths. It may be forcing distant objects to align their orbits within specific angular ranges. This directional clustering provides independent support for Planet 9's possible existence and helps astronomers narrow down where to search for it. The evidence keeps building in unusual ways. Not only do these distant objects point in similar directions, their orbital planes are also tilted at remarkably similar angles. This creates a 3-dimensional alignment that is hard to explain. Orbital planes are the flat surfaces that contain each object's path around the Sun. In a random system, these planes should be oriented every which way. Instead, they show systematic tilting patterns. The tilted orbits all lean in the same general direction through space. This reveals the 3-dimensional gravitational fingerprint of the hidden planet. It's not just affecting where objects point. It may also be controlling how their entire orbital planes are oriented. The mathematical precision of these tilted alignments provides powerful constraints on Planet 9's possible location and orbit. Astronomers can use this information to predict where the hidden world may be lurking. These tilted orbital planes represent one of the most sophisticated gravitational signatures of Planet 9's invisible influence. The final piece of evidence comes from objects so distant they exist in complete gravitational isolation from all known planets. These worlds lie beyond the reach of Neptune's influence. They should be free agents, following purely independent paths. Instead, these isolated worlds show the same mysterious alignments as objects closer to home. They appear to march in formation despite being completely cut off from known gravitational influences. This suggests something massive and distant may be influencing their motion. The isolation of these worlds makes their coordinated behavior even more remarkable. They can't be responding to Jupiter, Saturn, or Neptune. Those planets are simply too far away to have any effect. Only an undiscovered super-Earth in the outer solar system appears to explain their synchronized behavior this well. The gravitational reach of Planet 9 may extend so far that it influences objects even in the deepest isolation. These isolated worlds provide some of the strongest evidence that our solar system may contain a massive, hidden architectural force that has shaped the outer regions for billions of years. What happens when you roll dice and keep getting the same number? You check if the dice are loaded. Astronomers faced exactly this situation when they counted extreme objects in the outer solar system. More than a dozen of the most distant worlds cluster together in ways that violate basic probability. These objects should be scattered randomly throughout space. Instead, they huddle within narrow ranges of orbital direction. Scientists calculated the odds of this clustering happening by pure chance. The numbers came back essentially impossible. Imagine flipping a coin 20 times and getting heads every single time. That's still more likely than the orbital clustering astronomers discovered. The statistical evidence alone strongly suggests that some massive force is organizing these distant worlds into coordinated groups. This clustering represents the first concrete sign that an invisible shepherd may be guiding its flock through the outer darkness. Astronomers discovered something disturbing in the outer solar system. Certain distances from the Sun contain no objects at all. These regions should be populated with distant worlds. Instead, they're completely empty. These gaps occur at very specific distances from the Sun. Objects that wander into these zones can get ejected from the solar system entirely. Some invisible force seems to sweep them clean with ruthless efficiency. Scientists call these cleared regions resonant gaps. They form when objects orbit the Sun at precise mathematical relationships with a massive hidden planet. The gravitational interactions become so strong they destroy stable orbits. The pattern of gaps reveals the orbital period of the hidden planet. Only a world completing one orbit every 15,000 years could create exactly these forbidden zones. These empty regions provide a photographic negative of Planet 9's gravitational influence. They show us where it prevents objects from surviving rather than where it allows them to exist. Every extreme object in the outer solar system follows a highly stretched oval path around the Sun. But here's what makes this truly mysterious. They're all stretched in remarkably similar ways. Orbital eccentricity measures how oval-shaped a planet's path becomes. A perfect circle has zero eccentricity. These distant objects show eccentricities clustering around very specific values. The shared orbital shapes cannot be a coincidence. Some gravitational sculptor has been molding these paths for millions of years. The hidden planet acts like a cosmic pottery wheel, spinning distant objects into matching oval patterns. Computer models reveal why these shapes become so similar. The massive hidden world forces distant objects into stable gravitational relationships. Objects that don't conform to these shapes can get ejected from the solar system entirely. The matching orbital eccentricities provide a gravitational fingerprint of Planet 9's invisible artistry sculpting the outer solar system. Here's where the evidence becomes truly sophisticated. The tilt angles of distant orbits correlate directly with their pointing directions through space. Two completely independent orbital features move together in lockstep. Orbital inclination measures how much a planet's path tilts relative to Earth's orbital plane. Argument of perihelion measures which direction the orbit points. These should vary independently of each other. Instead, astronomers discovered a systematic relationship. Objects with certain tilt angles consistently point in specific directions. The correlation is too precise to be accidental. This relationship reveals the three-dimensional gravitational architecture of the outer solar system. The hidden planet doesn't just control where objects point or how they tilt. It controls both simultaneously through complex gravitational choreography. The correlated tilting and pointing strongly suggests that Planet 9 operates as a master gravitational conductor orchestrating multiple orbital elements in perfect harmony. Can distant objects communicate across billions of miles of empty space? In the outer solar system, they effectively do. Through gravitational resonance, widely separated worlds coordinate their orbital timing with mathematical precision. Resonance occurs when objects complete their orbits in simple numerical ratios. One object might orbit exactly twice while another orbits 3 times. These relationships create stable, long-term gravitational locks. The extreme outer solar system contains multiple resonant chains. Objects that should move independently instead march to synchronized gravitational rhythms. They maintain these relationships across cosmic timescales. The resonant chains require a massive organizing force. Only Planet 9 appears to have enough gravitational influence to establish and maintain these delicate orbital harmonies across such vast distances. These gravitational symphonies provide some of the strongest evidence, yet that our solar system contains a hidden conductor orchestrating cosmic music from the outer darkness. Some orbital features change so slowly they take millions of years to complete one cycle. These gradual transformations, called secular variations, preserve gravitational memories of ancient interactions. Secular resonance occurs when the slow, wobbling motions of different orbits synchronize over geological timescales. The orbital ellipses slowly rotate through space while maintaining precise relationships with each other. Distant objects in our solar system show clear patterns of secular resonance. Their orbital orientations drift through space in coordinated fashion. These slow dances reveal the long-term gravitational influence of Planet 9. The secular patterns provide a fossil record of gravitational interactions spanning millions of years. They suggest the hidden planet has been shaping the outer solar system since ancient times. These slow gravitational memories demonstrate that Planet 9 isn't a temporary visitor. It's likely been conducting orbital symphonies for cosmic ages. Astronomers discovered that distant objects naturally organize themselves into distinct orbital families. Each family shares similar characteristics and evolutionary histories. This family structure reveals how gravitational shepherding operates in practice. The scattered disk represents one such family. These objects follow highly elongated orbits that bring them close to Neptune before sending them far into space. Despite their chaotic-seeming paths, they show systematic patterns. Different orbital families occupy different regions of the outer solar system. The boundaries between families aren't random. They're determined by the gravitational influence of Planet 9. The hidden world sorts objects into distinct categories. This family structure shows that gravitational shepherding isn't just theoretical. It actively operates in our solar system, organizing distant worlds into coherent groups with shared characteristics. The scattered families demonstrate that Planet 9 functions as a cosmic immigration officer, determining which objects can live where in the outer solar system. Why don't these distant objects simply fly apart into space? The outer solar system should be a realm of chaos where small gravitational perturbations accumulate over time. Instead, it shows remarkable stability. Hill stability analysis reveals which orbital configurations can survive over billions of years. Most arrangements in the outer solar system should be fundamentally unstable. Objects should gradually drift away or get ejected entirely. The observed orbital arrangements violate these stability requirements. They maintain configurations that should collapse within millions of years. Some external force must be providing gravitational support. Planet 9 offers a solution to the stability paradox. Its massive gravitational presence creates stable zones where distant objects can survive for cosmic ages. Without this hidden anchor, the outer solar system would be far less orderly. The unusual stability of distant orbits strongly suggests that our solar system contains a massive hidden stabilizer that has preserved the outer architecture for billions of years. Astronomers measure the temperature of orbital systems by analyzing how spread out object velocities become. Hot systems have widely scattered velocities. Cold systems show tightly clustered speeds. The outer solar system shows a velocity distribution that's too hot to be in gravitational equilibrium. Objects move with more scattered velocities than they should if left alone. Some external source is continuously steering the system. This dynamical heating can only come from ongoing gravitational interactions. The scattered velocities suggest that distant objects regularly encounter strong gravitational perturbations from an unseen massive body. The velocity measurements provide an independent line of evidence for Planet 9's existence. The heating patterns match what scientists predict from a super-Earth in the outer solar system. These temperature signatures reveal that the outer solar system remains gravitationally active rather than settling into cold equilibrium. That points to a massive hidden world continuing to stir the cosmic pot. The ultimate test came when astronomers ran computer simulations forward through billions of years of cosmic evolution. Could they recreate the observed orbital patterns starting from random initial conditions? The simulations included every known gravitational influence in our solar system. Scientists let virtual planets and asteroids evolve through deep time. Without Planet 9, the results never matched reality. But when they added a massive hidden planet to their simulations, everything changed. The virtual solar system evolved into close agreement with observations. Random starting conditions organized themselves into the same broad patterns we see today. The billion-year simulations suggest that Planet 9 isn't just consistent with current observations. It may be necessary to explain how the outer solar system reached its present configuration. These computational experiments provide some of the strongest evidence that our solar system's architecture may require a massive hidden world that has been orchestrating gravitational evolution for cosmic ages. Planet 9 must be massive enough to control distant orbits, but small enough to remain invisible. This narrow requirement constrains its mass within very specific limits. Computer simulations reveal the hidden planet must weigh at least 5 times as much as Earth. Anything smaller lacks the gravitational strength to create observed orbital disturbances. But it cannot exceed half of Neptune's mass, or it would have been detected by now. This places Planet 9 in the super-Earth category. Super-Earths are planets larger than Earth but smaller than Neptune. They represent the most common type of planet in other solar systems. The mass range suggests Planet 9 formed as a planetary embryo during the solar system's early chaos. It grew large enough to become a major world, but never reached the size of the gas giants. This intermediate mass makes Planet 9 a cosmic exile. Too small to dominate like the gas giants, but too large to hide among the smaller worlds. Distance creates invisibility in space. Planet 9 orbits the Sun at such tremendous distances that it receives almost no sunlight and reflects virtually nothing back to Earth. The hidden planet likely orbits between 400 and 800 times farther from the Sun than Earth. At these distances, sunlight becomes incredibly faint. The Sun appears as just another bright star in Planet 9's alien sky. One complete orbit takes the planet roughly 15,000 Earth years. This means Planet 9 has completed only a tiny fraction of its orbit since the last ice age ended. Human civilization has existed for less than 1 planetary year. The extreme orbital period explains why Planet 9 remains undetected despite decades of sky surveys. It moves so slowly against the background stars that it appears stationary. Astronomers need years of observations to detect its motion. This glacially slow orbit makes Planet 9 a cosmic time capsule preserving conditions from the solar system's ancient past. Planet 9 likely resembles a smaller, colder version of Uranus or Neptune. Scientists classify these worlds as ice giants because they contain large amounts of water, methane, and ammonia ices mixed with rock and metal. The planet probably formed with a dense rocky core surrounded by thick layers of ice and compressed gases. Unlike the gas giants Jupiter and Saturn, ice giants have relatively thin atmospheric envelopes surrounding their solid interiors. At Planet 9's extreme distance, temperatures drop to only a few tens of degrees above absolute zero. Water freezes into rock-hard ice. Methane and ammonia solidify into exotic crystalline forms. The entire world becomes a frozen museum of primordial materials. These frigid conditions preserve the original composition from the solar system's formation. Planet 9 likely retains pristine samples of the ice and rock that built the outer solar system billions of years ago. The ice giant structure explains why Planet 9 gives off so little heat and remains difficult for infrared telescopes scanning the sky to detect. What kind of atmosphere exists on a world that receives 1/10,000th of Earth's sunlight? The answer involves extreme physics that transform gases into unusual states of matter. Any atmosphere on Planet 9 would consist primarily of hydrogen and helium captured during the planet's formation. But the extreme cold changes everything about how these gases behave. At temperatures only a few tens of degrees above absolute zero, atmospheric behavior becomes very different from what we know on Earth. Some gases can condense into liquid or freeze into solids under the right pressures. The atmospheric pressure might be so low that materials can pass directly between solid and vapor without lingering as liquids. Atmospheric circulation would be incredibly sluggish compared to Earth. Weather patterns might take centuries or millennia to develop and change. Storms could persist for geological timescales without dissipating. These alien atmospheric conditions create a world unlike anything else in our solar system, a place where the familiar rules of weather and climate break down completely. Planet 9 exists in the cosmic deep freeze. Surface temperatures probably hover around 40 degrees above absolute zero. At this temperature, familiar materials behave in completely alien ways. Nitrogen freezes solid at these temperatures. Carbon dioxide becomes harder than rock. Even gases like methane and ammonia transform into crystalline solids with properties unlike anything on Earth. The extreme cold means Planet 9 radiates very little thermal energy back to space. This makes the planet nearly invisible to infrared telescopes that detect heat signatures from distant objects. Seasonal temperature variations would be minimal, because the planet's orbit is so large that distance changes from the sun become insignificant. The world remains perpetually locked in cosmic winter. These frigid conditions create a planetary refrigerator that has preserved primordial materials in deep freeze for over 4 billion years. Despite its frozen exterior, Planet 9 likely generates a strong magnetic field through internal dynamics. The key lies in the planet's metallic core and slow internal convection processes. Ice giant planets contain dense interiors rich in heavy elements. Deep inside, electrically conducting material may remain mobile because internal heat from radioactive decay still escapes over time. That slow movement can support magnetic field generation. Moving conducting material acts like a giant electrical generator. The convection currents create electrical currents that generate powerful magnetic field lines extending far into space around the planet. A strong magnetic field would create a protective bubble around Planet 9, deflecting charged particles from the solar wind and cosmic radiation. This magnetosphere could extend for millions of miles around the planet. The magnetic field generation suggests that Planet 9 may remain internally dynamic despite its frozen appearance, a world with a beating electromagnetic heart. Planet 9's massive gravitational field has likely captured numerous small objects to create a complex system of moons and rings. These satellite systems form through gravitational interactions over cosmic timescales. The planet's large hill sphere, its region of gravitational dominance, extends far enough to capture passing objects from the Kuiper Belt and scattered disk. Once captured, these objects settle into stable orbits around the hidden giant. Captured satellites would include both icy bodies and rocky asteroids swept up during the planet's gravitational migration through the outer solar system. The satellite system preserves a record of Planet 9's orbital evolution. Ring systems could form when satellites venture too close to the planet and get torn apart by tidal forces. The debris spreads into thin rings of ice and rock particles orbiting the hidden world. This satellite system makes Planet 9 not just a single world, but the center of a complex gravitational community that has been evolving for billions of years. Planet 9's current orbit tells a story of violent gravitational exile from the inner solar system. The planet likely formed much closer to the Sun before being ejected by interactions with Jupiter and Saturn. During the solar system's chaotic early period, planetary embryos migrated through gravitational interactions with gas and other planets. Some embryos collided and merged. Others got ejected into the outer darkness. Planet 9 probably formed in the region where Uranus and Neptune now orbit. Gravitational encounters with Jupiter during a period called the Grand Tack may have sent the planetary embryo on a highly elongated orbit. Over millions of years, additional gravitational interactions gradually circularized the orbit at its current extreme distance. Planet 9 became a cosmic refugee, banished from the inner solar system to wander the outer darkness. This formation scenario explains why Planet 9 has the mass and composition of an ice giant but orbits far beyond the other giant planets in our solar system. Planet 9 reflects almost no sunlight back toward Earth, making it one of the darkest objects in the solar system. This low reflectivity, called albedo, results from its ancient surface composition and extreme environment. The planet's surface likely consists of organic compounds that form through radiation processing of methane and other carbon-bearing molecules. Over billions of years, cosmic radiation breaks down these compounds into complex dark materials. This process, called space weathering, turns initially bright icy surfaces into dark, reddish-brown materials that absorb most incoming light. Similar darkening affects many objects in the outer solar system. The combination of low albedo and extreme distance makes Planet 9 roughly 1 million times fainter than the dimmest objects visible to the naked eye. Even the most sensitive telescopes need long exposure times to detect such faint targets. This natural camouflage explains why Planet 9 has remained hidden despite extensive sky surveys. It's essentially a cosmic stealth bomber invisible to conventional detection methods. Planet 9 generates more heat internally than it receives from the Sun. This internal heat emission represents the best hope for detecting the hidden world through infrared astronomy. Radioactive decay within the planet's core produces steady heat that slowly leaks outward through the ice and rock layers. Additional heat comes from the gradual gravitational contraction of the planet itself. This internal heat makes Planet 9 slightly warmer than it would be from sunlight alone. The planet radiates this excess energy as infrared radiation, heat that sensitive telescopes can potentially detect. Tidal heating from gravitational interactions with captured satellites could provide additional internal energy. The flexing and stretching of the planet's interior converts orbital motion into heat through friction. This faint infrared glow represents Planet 9's only visible signature across the vast darkness of space, a cosmic lighthouse beacon waiting for astronomers to spot its feeble signal. Calculating how multiple planets influence each other gravitationally creates one of the most complex problems in physics. Scientists call this the N-body problem. The N represents however many objects you're tracking at once. Each planet pulls on every other planet simultaneously. Jupiter tugs on Saturn. Saturn pulls on Uranus. Uranus affects Neptune. All while the Sun dominates everything with its massive gravitational field. The mathematics becomes impossibly complex when you add more bodies to the calculation. There's no simple formula that works. Scientists must use numerical integration, essentially letting computers take millions of tiny mathematical steps forward through time. These supercomputer simulations can track gravitational interactions across billions of years. They reveal how adding one massive hidden planet changes everything in the outer solar system. The N-body calculations suggest that Planet 9's gravitational influence could propagate through the entire system, creating the orbital patterns we observe today. Why do tiny asteroids follow predictable paths when giant planets constantly tug on them? The answer lies in perturbation theory, a mathematical framework that breaks complex gravitational influences into manageable pieces. Lagrangian mechanics provides the mathematical language for describing these interactions. Named after mathematician Joseph Louis Lagrange, this approach treats planetary motion as an energy optimization problem. Small objects in the outer solar system experience constant gravitational perturbations from massive planets. These tiny pushes and pulls accumulate over millions of years. What seems like random wobbling actually follows precise mathematical patterns. Computer models use perturbation theory to predict exactly how Planet 9 should affect distant orbits. The calculations match observed orbital disturbances with stunning accuracy. This mathematical framework transforms Planet 9 from speculation into testable prediction, showing how an unseen super-Earth could be reshaping the outer solar system. Space contains invisible musical relationships played out through orbital motion. When planets orbit the Sun in simple numerical ratios, they create mean motion resonances, stable gravitational harmonies that can last for cosmic ages. A 2-to-1 resonance means one planet completes exactly 2 orbits while another completes one. A 3-to-2 resonance locks 3 orbits of one object to 2 orbits of another. These mathematical relationships create powerful gravitational effects. Resonances don't just happen randomly. They require precise orbital speeds and distances to establish and maintain. Once locked into resonance, objects resist gravitational perturbations that would otherwise destabilize their orbits. The outer solar system shows multiple resonant relationships that may be difficult to explain without a massive organizing force. Planet 9 could provide the gravitational influence needed to establish and maintain these cosmic harmonies. These resonant locks suggest that our solar system may contain a hidden conductor orchestrating mathematical symphonies across billions of miles of space. Here's something counterintuitive about orbital mechanics. An object's orbital shape and its tilted angle through space can become gravitationally connected. This coupling creates the Kozai resonance, a long-term oscillation that trades orbital eccentricity for orbital inclination. Orbital eccentricity measures how stretched an elliptical path becomes. Orbital inclination measures how much the orbital plane tilts relative to other planets. Normally, these two features vary independently. But when a massive distant planet exerts gravitational influence, it can couple these properties together. As an orbit becomes more circular, its tilt angle increases. As the tilt decreases, the orbit stretches into a longer ellipse. This oscillation occurs over millions of years, creating a slow gravitational dance between orbital shape and orientation. The Kozai mechanism requires a massive perturbing body to drive the coupling. The extreme outer solar system shows possible signs of Kozai oscillations, suggesting that Planet 9 may have been driving long-term orbital evolution for cosmic ages. Some gravitational effects work like compound interest in a bank account. Small changes accumulate slowly over enormous timescales until they create dramatic orbital transformations. Astronomers call these secular perturbations. Secular changes affect the orientation of orbital ellipses without changing their size or shape. The long axis of an orbit slowly rotates through space. The orbital plane gradually tilts and wobbles. These slow motions take tens of thousands of years to complete one cycle, They preserve gravitational memories of ancient planetary interactions. The current orientations of distant orbits reflect millions of years of accumulated secular effects. Planet 9 drives secular perturbations throughout the outer solar system. Its gravitational influence slowly rotates distant orbital ellipses into aligned configurations over geological timescales. These deep time accumulations suggest that a hidden planet may have been steadily organizing outer solar system architecture for cosmic ages. How do you know when gravitational interactions become chaotic and unpredictable? Mathematicians have developed chaos indicators, numerical tools that measure how sensitive orbital systems become to tiny changes in starting conditions. Chaotic systems amplify small differences exponentially over time. Two objects starting in nearly identical orbits can end up in completely different places after millions of years. This sensitivity to initial conditions defines mathematical chaos. Scientists use chaos indicators to test whether observed orbital configurations could survive over billion-year timescales. Most arrangements in the outer solar system should be fundamentally chaotic and unstable. Instead, the distant orbits show remarkably low chaos indicators. They follow stable, predictable paths despite existing in regions that should be gravitationally turbulent. Planet 9's proposed stabilizing influence reduces chaos throughout the outer solar system, creating islands of stability in what should be a sea of gravitational turbulence. Every orbit carries invisible mathematical constants that never change no matter how complex the gravitational interactions become. These orbital integrals, particularly energy and angular momentum, provide powerful constraints on possible orbital evolution. Total energy measures how much speed and gravitational potential an orbiting object possesses. Angular momentum measures the object's rotational motion around the central star. These quantities remain constant unless external forces add or remove them. Conservation laws allow scientists to trace orbital evolution backward and forward through billions of years. Objects can change their paths dramatically while still preserving their fundamental energy and angular momentum. Computer simulations use these conservation principles to verify that Planet 9 scenarios remain physically realistic over cosmic timescales. The hidden planet must preserve the total energy and angular momentum of the outer solar system. These mathematical constraints show that Planet 9 scenarios can operate within the fundamental laws of physics while dramatically reshaping distant orbital architecture. Every massive object claims gravitational territory around itself called a Hill sphere. Within this region, the object's gravity dominates over more distant gravitational influences. The Hill sphere determines which smaller objects a planet can capture and control. Hill sphere radius depends on a planet's mass and its distance from the Sun. More massive planets claim larger territories. Objects farther from the Sun can maintain larger gravitational domains. Planet 9's estimated mass and distance give it a Hill sphere stretching across enormous volumes of space. This gravitational territory encompasses the regions where astronomers observe strange orbital alignments. Objects entering Planet 9's Hill sphere experience strong gravitational steering. They can be captured into resonant orbits, ejected from the solar system, or guided into specific orbital families. Hill sphere analysis suggests that Planet 9 may possess the gravitational reach needed to control distant objects across the observed regions of orbital alignment. Can we predict where a distant object will be in a million years? The answer depends on Lyapunov exponents, mathematical measures of how quickly orbital uncertainty grows over time. Lyapunov exponents quantify the rate at which small orbital uncertainties expand into large unpredictabilities. Positive exponents indicate chaotic motion where long-term prediction becomes impossible. Negative exponents suggest stable, predictable behavior. Most regions of the outer solar system should have positive Lyapunov exponents, making long-term orbital evolution completely unpredictable. Objects should gradually drift into chaotic trajectories and get ejected from the solar system. Instead, observed orbits can show negative Lyapunov exponents in regions where Planet 9's gravity provides stabilizing influence. The hidden planet creates predictable orbital channels through otherwise chaotic space. These stability measures suggest that Planet 9 may function as a gravitational lighthouse, guiding distant objects along stable paths through the treacherous outer solar system. The ultimate tool for understanding complex orbital systems comes from Poincare sections, mathematical cross-sections that reveal hidden patterns in gravitational phase space. These diagrams transform chaotic-looking orbital motion into geometric structures. Phase space represents all possible orbital states an object can occupy. Position coordinates combine with velocity coordinates to create a multi-dimensional space of orbital possibilities. Poincare sections slice through this space at specific moments. Regular orbital motion creates smooth curves and islands in phase space. Chaotic motion produces scattered points and fractal boundaries. Resonant orbits appear as distinct geometric patterns with clear mathematical signatures. Phase space analysis reveals how Planet 9's gravity organizes the outer solar system into distinct regions of stability and chaos. Resonant islands appear exactly where the hidden planet should create stable orbital families. These mathematical maps suggest that Planet 9 may not just influence distant orbits randomly. It may create an elegant gravitational architecture that transforms chaotic space into organized cosmic neighborhoods. Imagine trying to spot a candle flame from 1,000 miles away. That's essentially what astronomers face when searching for Planet 9. The hidden world orbits at such extreme distances that even light takes hours to travel between the planet and Earth. Planet 9 likely orbits roughly 600 times farther from the Sun than Earth does. At this distance, sunlight becomes incredibly faint. The planet receives thousands of times less illumination than objects in the inner solar system. Light delay creates additional complications for observations. When astronomers point their telescopes toward Planet 9's predicted location, they're seeing where the planet was hours ago, not where it is now. This vast distance explains why Planet 9 remained hidden despite decades of sky surveys. The combination of extreme distance and faint illumination pushes the planet beyond the detection limits of most telescopes. Distance transforms Planet 9 from a massive world into a nearly invisible speck lost in the cosmic darkness. How small can something appear before it becomes invisible? Planet 9 tests this limit by appearing smaller than a pinhead viewed from across a football stadium. Angular size measures how much space an object occupies in the sky as seen from Earth. The Moon appears large because it's relatively close to us. Distant objects appear progressively smaller until they become indistinguishable points. Even though Planet 9 might be several times larger than Earth, its extreme distance shrinks it to an angular size measured in tiny fractions of an arcsecond. An arcsecond is 1/3600th of a degree, already an incredibly small unit. The most powerful telescopes can barely resolve objects this small. Planet 9 likely appears as a single pixel or less on even the largest telescope cameras. There's no way to see any surface features or determine its shape. This microscopic angular size makes Planet 9 indistinguishable from countless other faint points of light scattered across the sky. Planet 9 reflects so little sunlight that it challenges the fundamental limits of what telescopes can detect. The planet appears roughly 1 million times fainter than the dimmest stars visible to the naked eye. Brightness in astronomy is measured using the magnitude scale. Each increase of 5 magnitudes represents a 100-fold decrease in brightness. Planet 9 likely shines at magnitude 25 or fainter. current telescope technology can detect objects down to roughly magnitude 27 under perfect conditions. This places Planet 9 right at the edge of detectability. Any clouds, atmospheric turbulence, or electronic noise could hide the planet's faint signal. The extreme faintness means telescopes need very long exposure times to collect enough photons to register Planet 9's presence. These lengthy observations increase the chances of interference from cosmic rays, satellite trails, and other sources of noise. Planet 9's faintness transforms the search from routine observation into an extreme test of technological limits. How do you tell the difference between a distant planet and a background star? The answer lies in proper motion. The tiny shift in position that planets show as they orbit the Sun. Proper motion measures how much an object appears to move across the sky over time. Nearby stars show measurable proper motion as they travel through space. Background stars appear stationary. Planets show orbital motion around the Sun. Planet 9's orbital motion is incredibly slow because of its extreme distance from the Sun. The planet might move only a few arcseconds per year against the background stars. This motion is so small it requires multiple years of observations to detect with confidence. Astronomers must take photographs of the same region of sky repeatedly over several years. They then compare these images using computer algorithms that can detect tiny shifts in object positions. The slow proper motion means discovering Planet 9 requires extraordinary patience and long-term commitment to sustained observations. Planet 9 could be hiding anywhere within a region of sky larger than the full moon. This positional uncertainty turns the search into a cosmic needle in a haystack problem of staggering proportions. Orbital calculations based on gravitational disturbances provide only approximate predictions for Planet 9's current location. These uncertainties arise from measurement errors in distant object orbits and assumptions about the planet's exact mass and orbital parameters. The search region covers hundreds of square degrees of sky. For comparison, the full moon occupies only half a degree. Astronomers must systematically survey this entire region to have any hope of finding the hidden planet. Each small section of sky requires multiple observations over several years to detect proper motion. The vast search area multiplies the required observation time by hundreds of factors. This enormous search zone explains why Planet 9 hasn't been found yet despite intensive efforts by multiple research teams around the world. Planet 9 must hide among roughly 100 million background stars visible in deep telescope images. This creates an identification challenge unlike anything else in astronomy. Deep sky surveys capture millions of faint stars in each telescope field. Every one of these stellar images could potentially be Planet 9 masquerading as a star. Astronomers must examine each point of light for signs of planetary motion. Background stars vary in brightness and color in ways that can mimic planetary properties. Some stars pulsate, creating brightness changes that might be confused with orbital variations. Others form close pairs that appear as single fuzzy objects. Computer algorithms help astronomers filter out obvious stars by analyzing color, brightness patterns, and motion characteristics. But these automated systems still leave thousands of ambiguous candidates requiring individual examination. The stellar background transforms Planet 9 detection from simple observation into a massive data analysis challenge requiring sophisticated computer processing. Earth's atmosphere constantly churns and shifts, blurring telescope images and scattering faint light signals. This atmospheric turbulence, called seeing, poses a major obstacle to detecting extremely faint objects like Planet 9. Atmospheric seeing causes stars to appear as fuzzy disks rather than sharp points. The size of these seeing disks varies from night to night depending on atmospheric conditions. Poor seeing can make faint objects completely disappear into background noise. Temperature differences in the atmosphere create cells of moving air that act like shifting lenses. These atmospheric lenses constantly redirect and scatter light from distant objects. Planet Nine's already faint signal gets further weakened by this atmospheric interference. Ground-based telescopes must wait for exceptional seeing conditions to have any chance of detecting Planet Nine. These perfect nights occur only rarely at most observatory sites. Cloud cover and weather further reduce available observing time. Space-based telescopes avoid atmospheric problems entirely, making them potentially more effective for Planet Nine searches despite their smaller sizes compared to ground-based giants. Surveying the entire search region for Planet Nine using a single telescope would require several decades of continuous observation time. This enormous time requirement pushes the search beyond what any individual observatory can accomplish. Modern digital sky surveys can photograph large areas of sky in single exposures. But even the most efficient surveys need multiple observations of each region over several years to detect slow-moving objects. The total sky area that might contain Planet Nine covers roughly 10% of the entire celestial sphere. Systematic surveys of this region require hundreds of clear nights spread over many years. Weather, equipment failures, and competing research priorities limit the actual observing time available for Planet Nine searches. Most large telescopes can dedicate only a small fraction of their time to any single research program. This observational bottleneck explains why collaborative efforts involving multiple telescopes and research teams are essential for mounting effective Planet Nine search campaigns. Once astronomers find Planet Nine, they'll need to analyze its light spectrum to determine the planet's composition and atmospheric properties. Spectroanalysis breaks down planetary light into its component wavelengths like a prism creating a rainbow. Different molecules absorb light at specific wavelengths, creating dark lines in the spectrum called absorption features. These spectral fingerprints reveal which gases exist in Planet Nine's atmosphere and surface composition. The extreme faintness of Planet Nine makes spectral analysis incredibly challenging. Collecting enough photons to create a useful spectrum might require dozens of hours of observation time on the world's largest telescopes. Atmospheric absorption lines from water vapor, methane, and other molecules could provide crucial clues about Planet Nine's formation history and internal structure. These spectral details would confirm whether the planet matches theoretical predictions for ice giant composition. Spectral analysis represents the final step in transforming Planet Nine from a mysterious gravitational influence into a fully characterized world with known physical and chemical properties. Finding a candidate object is only the beginning of Planet Nine discovery. Confirming that a faint point of light is actually the hidden planet requires years of careful, follow-up observations and orbital analysis. Initial discovery images must be verified through independent observations at different telescopes. False detections can arise from cosmic ray hits, instrumental artifacts, or processing errors. Multiple confirmations eliminate these false positives. Orbital determination requires tracking the candidate object's motion over several years. Astronomers must measure precise positions in dozens of follow-up images to calculate orbital elements with sufficient accuracy. The orbital solution must match theoretical predictions for Planet Nine's mass, distance, and gravitational effects on other solar system objects. Any significant discrepancies would suggest the candidate is actually a different type of object. Follow-up spectroscopy would provide the final confirmation by revealing Planet Nine's physical properties and composition. Only after completing this extensive verification process can astronomers confidently announce the discovery of the solar system's ninth planet. Modern astronomy requires telescopes that can photograph vast areas of sky in single exposures. The Subaru telescope in Hawaii represents one of the most powerful tools in this cosmic search effort. Subaru's unique design combines a massive 8-meter mirror with an ultra-wide field camera system. This combination allows astronomers to capture sky regions dozens of times larger than what traditional telescopes can observe at once. The telescope's wide field capability means it can survey Planet 9's entire predicted search region in a fraction of the time required by conventional instruments. Instead of taking thousands of individual exposures, Subaru can cover the same area with just dozens of images. High-sensitivity detectors capture incredibly faint objects that would be invisible to smaller telescopes. These digital cameras can record objects millions of times fainter than anything visible to the naked eye. This wide-field surveying power transforms Planet 9 searches from decades-long projects into systematic campaigns that can be completed within a few years of dedicated observing time. What if Planet 9 glows too faintly in visible light but radiates detectable heat? NASA's WASP mission, the Wide Field Infrared Survey Explorer, searched for exactly this type of thermal signature from space. WASP operated as a space-based infrared telescope that scanned the entire sky multiple times between 2010 and 2011. Infrared light reveals the heat that objects radiate naturally, rather than the reflected sunlight that optical telescopes detect. Space-based observations avoid the atmospheric interference that limits ground-based infrared astronomy. Earth's atmosphere absorbs most infrared radiation, making space the ideal platform for thermal detection of cold, distant objects. The mission cataloged over 500 million infrared sources across the sky. Computer algorithms searched this vast database for objects showing the slow motion characteristic of distant planets orbiting the Sun. Although WASP didn't find Planet 9, its systematic sky survey placed important limits on how bright the planet could be in infrared light, constraints that help astronomers refine their search strategies. Can ordinary people help discover new planets? Several citizen science projects have transformed planet hunting into collaborative efforts involving thousands of volunteers around the world. Projects like Backyard Worlds, Planet 9 present telescope images to volunteers through web-based interfaces that look like interactive puzzles. Participants examine pairs of sky images taken months or years apart, looking for objects that appear to move between the frames. Human pattern recognition excels at tasks that challenge even sophisticated computer algorithms. People can quickly spot subtle differences in image quality, cosmic ray artifacts, and other false signals that might fool automated detection systems. The distributed effort multiplies the effective analysis power available for Planet 9 searches. Thousands of volunteers can examine sky survey data far more quickly than small teams of professional astronomers working alone. These crowdsourced searches have already discovered dozens of nearby brown dwarfs and other faint objects, proving that citizen science represents a powerful tool for astronomical discovery. Modern sky surveys generate so much data that human analysis becomes impossible. Machine learning algorithms now provide the computational power needed to process billions of astronomical images automatically. Artificial intelligence systems learn to recognize planetary motion by training on datasets containing thousands of known moving objects. These algorithms develop pattern recognition capabilities that can identify subtle motion signatures invisible to manual inspection. Deep learning networks analyze multiple image features simultaneously. Brightness variations, color changes, motion patterns, and background contamination. This multi-dimensional analysis provides far more reliable object classification than simple motion detection alone. The algorithms can process years of sky survey data in just days or weeks of computer time. This computational speed allows astronomers to search much larger sky regions and examine longer time baselines than ever before possible. Machine learning transforms Planet 9 searches from labor-intensive manual efforts into automated data mining operations capable of handling the massive datasets produced by modern digital sky surveys. Finding moving objects requires comparing images of the same sky region taken at different times. Time-domain astronomy networks specialize in exactly this type of repetitive monitoring campaign. Modern digital cameras can photograph the same sky regions dozens of times per year over multiple years. This creates detailed time series data that reveals how object positions and brightness change over cosmic time scales. Automated telescopes operate robotically, returning to predetermined sky coordinates night after night with mechanical precision. Weather interruptions and seasonal visibility windows are automatically compensated by extending observation campaigns across multiple years. Time-domain networks coordinate observations between multiple telescopes at different geographic locations. This global approach ensures continuous sky coverage despite local weather conditions and daylight limitations at individual sites. These sustained monitoring campaigns provide the long temporal baseline needed to detect Planet 9's incredibly slow motion against the background star field. Planet 9 might be hiding in southern sky regions invisible to Northern Hemisphere telescopes. Major observatories in Chile and Australia provide crucial coverage of these otherwise inaccessible celestial territories. The Southern Hemisphere hosts some of the world's most advanced astronomical facilities, including the European Southern Observatory in Chile and the Anglo-Australian Telescope. These instruments can observe sky regions that never rise above the horizon for northern observatories. Atmospheric conditions at southern sites often surpass those available in the north. The Atacama Desert in Chile provides some of the clearest, dry skies on Earth, ideal for detecting extremely faint objects like Planet 9. International collaboration between northern and southern observatories ensures complete sky coverage for Planet 9 searches. No potential hiding spots remain unmonitored when global telescope networks coordinate their observation strategies. Southern sky surveys have already discovered numerous distant objects in regions where Planet 9 might lurk, proving the importance of hemispheric coverage for comprehensive solar system exploration. Revolutionary new telescopes now under construction will provide unprecedented capabilities for Planet 9 detection. The Vera Rubin Observatory and James Webb Space Telescope represent the next generation of astronomical discovery machines. The Vera Rubin Observatory will conduct the Legacy Survey of Space and Time, a 10-year program to photograph the entire visible sky every 3 nights. This rapid survey cadence will detect moving objects much more efficiently than current programs. The observatory's enormous digital camera contains over 3 billion pixels, the largest camera ever built for astronomy. Each image will capture sky regions 40 times larger than the full moon with exquisite sensitivity to faint objects. The James Webb Space Telescope brings unprecedented infrared sensitivity from its position in space. Its advanced instruments can detect thermal radiation from objects far colder and more distant than anything accessible to previous missions. These next-generation facilities will either discover Planet 9 definitively or place such stringent limits on its properties that alternative theories for outer solar system dynamics must be considered seriously. How do you distinguish a real planet detection from the millions of false signals generated by cosmic rays, instrumental artifacts, and data processing errors? Advanced statistical methods provide the answer through rigorous significance testing. False detection rates in astronomical surveys can reach thousands of candidates per night of observation. Most apparent moving objects turn out to be asteroids, cosmic ray hits, or processing artifacts rather than distant planets. Statistical algorithms calculate the probability that any particular detection represents a real astronomical object rather than random noise. These calculations consider factors like signal brightness, motion characteristics, and consistency across multiple observations. Machine learning classifiers trained on known object types can automatically reject obvious false detections while flagging ambiguous candidates for human review. This filtering reduces manual verification workload by factors of hundreds or thousands. Only detections that pass multiple statistical significance tests advance to the intensive follow-up observations required for planetary confirmation, ensuring that precious telescope time gets allocated to the most promising candidates. Planet 9 searches require more telescope resources than any single institution can provide. International collaboration networks pool observational capabilities and share data across institutional boundaries. Major sky survey projects involve dozens of institutions across multiple continents. These collaborations coordinate observation schedules, share telescope access, and combine data from different instruments to create comprehensive sky monitoring programs. Data sharing agreements ensure that Planet 9 candidates discovered by one team can be quickly verified by independent observers using different telescopes. This collaborative approach eliminates false discoveries while accelerating genuine confirmations. Standardized data formats and analysis pipelines allow different research groups to compare results and combine datasets. These technical standards prevent duplication of effort while ensuring that no potential discoveries fall through institutional cracks. Global collaboration multiplies the effective observing power available for Planet 9 searches while providing the redundancy needed to confirm one of the most important astronomical discoveries of the century. Finding a candidate object represents only the beginning of Planet 9 discovery. Rigorous verification protocols must confirm that faint moving points represent genuine planets, rather than false detections or misidentified objects. Independent confirmation requires detecting the same object using different telescopes, cameras, and analysis methods. Multiple independent detections eliminate false alarms caused by instrumental artifacts or data processing errors. Orbital analysis must demonstrate that the candidate follows a gravitationally bound orbit around the Sun with characteristics matching theoretical predictions for Planet 9. Objects on escape trajectories or with impossible orbital elements cannot be planets. Photometric measurements reveal object colors and brightness variations that distinguish planets from asteroids, brown dwarfs, and background stars. Planetary candidates must show colors consistent with ice-rich compositions and stable thermal emission. Only after passing all verification criteria can astronomers confidently announce Planet 9's discovery, transforming decades of theoretical speculation and observational effort into confirmed knowledge of our solar system's most elusive member. Could a tiny black hole be masquerading as Planet 9? Some scientists propose that primordial black holes, ancient cosmic monsters left over from the universe's earliest moments, might explain the mysterious gravitational effects in our outer solar system. Primordial black holes formed during the first fraction of a second after the Big Bang. These objects differ completely from the massive black holes that form when giant stars collapse. They could be as small as marbles but still contain several times Earth's mass. A primordial black hole with 5 times Earth's mass would create exactly the same gravitational disturbances that scientists attribute to Planet 9. The invisible object would tug on distant orbits in identical ways regardless of whether it is a planet or a black hole. The black hole scenario explains why searchers have not found Planet 9 despite years of intensive effort. Black holes emit no light and reflect no sunlight. They remain completely invisible except for their gravitational influence on nearby objects. This alternative theory transforms the search from hunting for a faint planet into detecting one of the universe's most exotic objects lurking at the edge of our cosmic neighborhood. What if there is no single massive object controlling the outer solar system? The collective gravity hypothesis suggests that many smaller bodies working together could create the same gravitational effects attributed to Planet 9. Instead of one super-Earth, this theory proposes that dozens of objects, each weighing roughly as much as Pluto, could be scattered throughout the outer solar system. Their combined gravitational influence might mimic the signature of a single massive planet. Computer simulations show that collective gravity can reproduce some aspects of the observed orbital alignments. Multiple small objects could nudge distant orbits into coordinated patterns through their combined gravitational tugging over millions of years. The collective scenario faces a major challenge. Astronomers would have already discovered objects as large as Pluto if they existed in the numbers required. Sky surveys have mapped most Pluto-sized bodies within the distances where collective gravity would be effective. This distributed mass theory requires hiding dozens of large objects in regions where intensive searches have found nothing, making it less plausible than a single hidden super-Earth. Scientists sometimes discover patterns in data that reflect the limitations of their instruments rather than real phenomena in nature. Could the Planet 9 evidence result from observational bias rather than genuine gravitational effects? Observational bias occurs when the methods used to find and study objects systematically favor certain types of discoveries. Telescopes point towards specific sky regions during certain seasons. Survey strategies focus on particular distance ranges and orbital orientations. Most extreme outer solar system objects were discovered by surveys that concentrated on specific parts of the sky where detection was easier. These surveys avoided regions close to the Milky Way where background stars make faint object detection nearly impossible. If Planet 9 does not exist, then the apparent orbital clustering might simply reflect which parts of the sky astronomers have searched most thoroughly. The missing objects in other sky regions might remain undiscovered rather than being genuinely absent. However, statistical analysis suggests that observational bias alone cannot account for the degree of clustering observed in distant orbits, supporting the need for a genuine gravitational explanation like Planet 9. How many distant objects do you need to observe before claiming you have found a real pattern? The statistical coincidence challenge argues that current orbital alignments might be random flukes, rather than evidence for Planet 9. Scientists have discovered only about 20 objects in the extreme outer solar system. This small sample size makes it difficult to distinguish genuine patterns from random coincidences that could occur by pure chance. Statistical significance calculations attempt to determine the probability that observed clustering could arise randomly. Different analysis methods produce different probability estimates, ranging from highly significant to marginally convincing. The debate centers on which statistical tests are most appropriate for analyzing orbital data. Some methods account for observational biases and selection effects. Others focus on the raw clustering patterns without corrections. As astronomers discover more extreme outer solar system objects, the statistical significance of any genuine clustering should increase, while random coincidences should gradually disappear into statistical noise. What if the problem is not missing planets but incomplete understanding of gravity? Modified gravity theories propose that Newton's and Einstein's laws break down at the extreme distances where Planet 9's effects are observed. Standard gravity follows an inverse square law. Gravitational force decreases with the square of the distance between objects. Modified gravity theories suggest this relationship might change at very large distances or very weak field strengths. Several theoretical frameworks propose modifications to gravity that could create Planet 9-like effects without requiring any massive hidden object. These theories predict that distant orbits should cluster naturally due to altered gravitational dynamics. modified gravity faces significant challenges from other astronomical observations. The same theories that might explain outer solar system clustering often conflict with observations of galaxy rotation curves, gravitational lensing, and cosmic structure formation. Most physicists consider modified gravity a less likely explanation than hidden planets, because it requires fundamental changes to well-tested physical laws that successfully explain countless other phenomena. Could a concentrated blob of dark matter be creating Planet 9's gravitational effects? Dark matter represents roughly 85% of all matter in the universe, yet it interacts only through gravity. Dark matter clumps could theoretically concentrate enough mass in small regions to create planet-like gravitational influences. A dark matter halo containing several Earth masses might produce the same orbital disturbances attributed to Planet 9. This scenario would explain why searchers have not found Planet 9 despite its obvious gravitational effects. Dark matter remains completely invisible to all electromagnetic radiation. No telescope could ever detect it directly. However, dark matter clumps face severe theoretical problems in the outer solar system. The material should have been dispersed by galactic tides and stellar encounters over billions of years. Maintaining a concentrated clump at Planet 9's distance requires special circumstances. Most dark matter models predict that any primordial clumps in our solar system would have been destroyed long ago, making this explanation less plausible than conventional planetary scenarios. Perhaps the outer solar system organized itself into current patterns through natural evolutionary processes that do not require Planet 9. Kuiper Belt evolution models explore how gravitational chaos might create apparent order over cosmic time scales. The early solar system experienced a period of intense gravitational chaos when the giant planets migrated to their current orbits. This chaotic phase scattered objects throughout the outer regions while creating complex dynamical structures. Some evolution models suggest that objects naturally cluster into stable orbital families during chaotic evolution. Initial random distributions could evolve into the patterns we observe today without requiring any massive hidden perturber. These models face the challenge of explaining why clustering persists over billions of years. Most chaotic systems tend toward randomization rather than maintaining organized structures. Special initial conditions are often required to produce current observations. Detailed computer simulations of Kuiper Belt evolution generally require additional massive objects, like Planet 9, to reproduce the observed orbital architecture, supporting planetary rather than purely evolutionary explanations. Could the entire Planet 9 phenomenon result from accumulated errors in measuring distant object orbits? The observational error hypothesis suggests that measurement uncertainties might create false patterns in orbital data. Determining accurate orbits for extremely distant objects requires decades of precise observations. Small errors in position measurements can accumulate into large uncertainties in calculated orbital parameters like eccentricity and inclination. Systematic errors in different telescope systems might bias orbital measurements in consistent directions. If multiple surveys share similar systematic errors, they could create artificial clustering patterns in the combined dataset. The error hypothesis predicts that improved measurements should gradually eliminate apparent orbital clustering. Better telescopes, longer observational baselines, and more sophisticated analysis techniques should reveal the patterns as instrumental artifacts. However, independent observations using different telescopes and measurement techniques continue to confirm orbital clustering, suggesting that systematic errors alone cannot explain the Planet 9 evidence. Massive collisions in the early solar system could have ejected material that still influences outer region dynamics today. Ancient collision theory proposes that catastrophic impacts created the gravitational disturbances attributed to Planet 9. During the solar system's violent first billion years, planetary embryos regularly collided with each other and with the growing giant planets. These impacts ejected massive amounts of material into distant orbits around the Sun. Some collision scenarios create populations of ejected objects that maintain coherent orbital properties for billions of years. These collision fragments might cluster in ways that mimic the gravitational influence of a single massive planet. The collision theory explains Planet 9's gravitational effects without requiring any currently existing massive object. The disturbing influence comes from ancient debris fields rather than a single concentrated world. However, collision models face difficulties explaining the precise orbital alignments observed in the outer solar system, patterns that require ongoing gravitational shepherding rather than ancient one-time events. Modern astronomy generates enormous datasets containing millions of measurements and observations. These vast databases can harbor misleading correlations that appear significant but actually represent meaningless statistical artifacts. Data mining involves searching large datasets for unexpected patterns and relationships. While this approach can reveal genuine discoveries, it also increases the chances of finding false correlations that arise purely by chance. The more patterns scientists look for in a dataset, the more likely they become to find spurious correlations. Multiple hypothesis testing requires increasingly stringent statistical standards to distinguish real discoveries from random fluctuations. Planet 9 evidence comes from analyzing orbital parameters of only about 20 objects. With so many ways to slice and analyze this small dataset, some correlations might be artifacts of the analysis methods rather than genuine physical phenomena. Rigorous statistical protocols attempt to account for multiple testing effects and data mining biases, but the debate continues over whether Planet 9's evidence meets the most stringent standards for avoiding false discovery traps. Discovering Planet 9 would force astronomers to redefine what counts as a major planet in our solar system. The current count of 8 planets has remained stable since Pluto's reclassification in 2006, but Planet 9 would shatter this cosmic status quo. The International Astronomical Union, the organization that officially defines planets, would need to establish new criteria for objects in the outer solar system. Planet 9's extreme orbit and massive gravitational influence do not fit existing planetary categories. Current planetary definitions assume that major planets orbit relatively close to the Sun and have cleared their orbital neighborhoods of debris. Planet 9 challenges both assumptions by orbiting in the distant Kuiper Belt while controlling vast regions through gravitational resonance. The discovery would create a new class of planet, super-Earths in highly eccentric orbits that govern outer solar system dynamics. This planetary category does not exist in current classification systems but appears common around other stars. Planet 9's confirmation would establish our solar system as containing 9 official planets once again, but with a completely new understanding of what planetary status means in the modern era. Planet 9's existence would revolutionize theories about how our solar system formed and evolved over billions of years. Current formation models struggle to explain how a massive planet could end up in such an extreme orbit. Solar system formation models describe how planets grew from dust and gas in a rotating disk around the young Sun. These models predict that large planets should form closer to the star, where more material was available for planetary construction. Planet 9's distant orbit suggests it formed much closer to the Sun before being ejected outward by gravitational interactions with Jupiter and Saturn. This migration process would have been violent and chaotic, reshaping the entire outer solar system. The discovery would confirm that planetary systems undergo dramatic reorganization phases after their initial formation. These migration events could explain many puzzling features of our solar system's architecture. understanding Planet Nine's formation would provide crucial insights into how planetary systems evolve. Knowledge essential for interpreting observations of planets around other stars where similar migration processes might occur. Planet Nine's gravitational field could capture numerous small moons that might harbor conditions suitable for life. These satellite worlds could contain liquid water oceans beneath their frozen surfaces, creating potential habitats in the outer solar system. Tidal heating occurs when a moon's orbit stretches and compresses the satellite as it travels around its parent planet. This gravitational flexing generates internal heat that can melt subsurface ice into liquid water oceans. Jupiter's moon Europa and Saturn's moon Enceladus both contain subsurface oceans maintained by tidal heating. Planet Nine's massive gravitational field could create similar conditions in any moons that orbit the hidden giant. These potential ocean worlds would exist in the habitable zone defined by tidal heating rather than solar radiation. Life in such environments would depend on chemical energy rather than sunlight for survival. Discovering Planet Nine would instantly expand the search for life to include an entirely new category of potentially habitable worlds located in the cold outer reaches of our solar system. Confirming Planet Nine would create the ultimate target for robotic space exploration, a journey to the edge of our solar system that would test the limits of current spacecraft technology. A mission to Planet Nine would require revolutionary advances in propulsion systems and navigation techniques. Current spacecraft technology cannot reach Planet Nine within reasonable mission timelines using conventional chemical rockets. Nuclear propulsion systems or solar sails might enable spacecraft to reach Planet Nine within several decades of travel time. These missions would pioneer the technologies needed for eventual interstellar exploration beyond our solar system. Planet Nine orbits at distances where the Sun appears as just another star in the sky. Spacecraft visiting this region would experience conditions similar to interstellar space while still remaining gravitationally bound to our solar system. These missions would provide humanity's first direct observations of objects in the transition zone between our solar system and the vast emptiness of interstellar space. Planet Nine represents a type of world that appears incredibly common around other stars but was missing from our own solar system. Super-Earths, planets larger than Earth but smaller than Neptune, represent the most frequent planetary type discovered by exoplanet surveys. Thousands of super-Earths have been discovered orbiting other stars, yet our solar system appeared to lack any examples of this planetary category. Planet Nine would fill this gap and provide a nearby laboratory for studying super-Earth properties. Direct study of Planet Nine would reveal crucial information about super-Earth composition, atmospheric properties, and formation mechanisms that cannot be obtained from distant exoplanets around other stars. The discovery would confirm that our solar system contains examples of all major planetary types found throughout the galaxy. This would validate using our solar system as a template for understanding planetary system architecture in general. Planet Nine would become the closest super-Earth available for detailed study, providing ground truth data for interpreting observations of similar planets discovered around thousands of other stars. Planet Nine's extreme orbital characteristics would create natural laboratory conditions for testing Einstein's theory of general relativity in the weak gravitational fields of the outer solar system. General relativity predicts that massive objects slightly bend the fabric of space-time around them. These effects become measurable in strong gravitational fields near black holes and neutron stars, but remain incredibly subtle in normal planetary environments. Planet Nine's large mass and eccentric orbit would create the strongest accessible gravitational field variations in the outer solar system. Precise tracking of the planet's orbital motion could reveal relativistic effects invisible in inner planetary orbits. The orbital precession, a gradual shift in the planet's orbital orientation, would include tiny contributions from general relativity that could be measured using advanced tracking techniques developed for gravitational wave detection. These measurements would provide the most precise tests of Einstein's theory possible within our solar system, potentially revealing new physics or confirming general relativity in previously untested regimes. Planet 9's discovery would drive development of new mathematical techniques for solving complex gravitational interactions between multiple massive objects. These computational advances would revolutionize celestial mechanics as a field. The n-body problem, calculating how multiple objects influence each other gravitationally, becomes exponentially more complex as additional massive bodies are included. Planet 9 would add new layers of complexity to outer solar system dynamics. Current computer simulations of solar system evolution struggle with the computational demands of tracking millions of small objects under the gravitational influence of multiple giant planets over billion-year timescales. Planet 9 would necessitate development of new computational algorithms and mathematical approximation techniques to handle the increased complexity. These advances would benefit fields ranging from spacecraft navigation to galaxy formation modeling. The mathematical tools developed for Planet 9 studies would find applications throughout astronomy and physics, advancing our ability to model complex systems with multiple interacting components. The observational techniques developed for finding Planet 9 will revolutionize the search for Earth-like planets around nearby stars. These technological advances will directly benefit the search for potentially habitable exoplanets. Planet 9 represents one of the faintest objects that ground-based telescopes can realistically detect. The sensitivity improvements and data analysis techniques required for its discovery push observational astronomy to new limits. Advanced image processing algorithms developed for Planet 9 searches automatically identify faint moving objects in massive astronomical datasets. These same techniques will enable detection of Earth-sized planets in the habitable zones of nearby stars. The statistical methods used to confirm Planet 9's reality while rejecting false detections will establish new standards for validating exoplanet discoveries. These rigorous verification protocols will reduce false discovery rates in future surveys. Planet 9 detection technology will provide the foundation for next-generation space missions designed to directly image and characterize potentially habitable worlds orbiting the closest stars to our solar system. Planet 9's discovery would force astronomers to reconsider where our solar system's gravitational influence ends and interstellar space begins. The traditional boundary definitions become inadequate when applied to objects in such extreme orbits. The heliopause, where the solar wind meets interstellar space, has long been considered the outer boundary of our solar system, but Planet 9's orbit extends far beyond this boundary into regions dominated by galactic gravitational influences. Gravitational sphere of influence calculations determine how far the Sun's gravity remains dominant over stellar and galactic forces. Planet 9 would orbit near or beyond this fundamental gravitational boundary. The discovery would establish new categories for solar system regions. The classical planetary zone, the Kuiper Belt and scattered disk, and the extreme outer region where Planet 9 resides at the edge of solar gravitational control. These new boundary definitions would influence how we classify objects around other stars and understand the transition zones between planetary systems and interstellar space. Planet 9's existence would provide crucial data for understanding how common unusual planetary configurations might be throughout the universe. This information would reshape models of cosmic planet formation and evolution. Current cosmological models predict the statistical properties of planetary systems based on the physics of star and planet formation. These models must explain the observed diversity of planetary architectures discovered around other stars. Planet 9 would demonstrate that even apparently normal planetary systems can harbor hidden giant planets in extreme orbits. This would suggest that many other planetary systems might contain undetected massive worlds. The discovery would influence estimates of how many planets exist in our galaxy and universe. If hidden super-Earths are common, the total planetary census could be much higher than current estimates suggest. Understanding Planet 9's place in cosmic planetary demographics would help astronomers predict what types of planetary systems should exist around different types of stars, guiding future searches for habitable worlds throughout the galaxy.